And we have a few comments on MapReduce and parallel computing. Already pointed this out that MapReduce is actually a well-known concept for some time. It was put together in a very clever, effective way and by people at Google, led by Geoffrey, but the general concepts have been well known in parallel computing for a while. And then we have the one model is that used in simulations, which run jobs. Each job has a lot of cores and a lot of nodes. They need very high performance networking to support the simulation. In the case of clouds, you're running a different class of job, either largely map-only jobs with very little communication, or cases where they're large messages which can be run efficiently on cloud technology. And as well as that MapReduce, we have iterative MapReduce we already mentioned, which is sort of halfway between the technology used in high-performance computing, which is called Message Passing Interface, MPI, and MapReduce, which is originally developed for a lot of search and other e-commerce applications. So MapReduce is sort of illustrated here. You have data stored on disks. It's fetched from disks. It's run through these maps. Remember, this map is part of the pipeline. We're running our data through a filter to convert it into information, or we're taking information and converting it into a different form of information or into knowledge. Then each part of the data is analyzed independently. If you have your data is the world's crawled web, those different crawlings and different parts of the web can be analyzed independently for a query. Then after you've analyzed each of those queries from parts of the data, parts of the world's web independently, you need to link them all together, which is the reduction operation, which takes the results of the independent map processes analyzing the search on different parts of the web and joins them together and actually applies the ranking to get you what it presents to the user. And then you can have more complicated cases, which what iterative MapReduce does. Instead of having the pipeline that like this, where these are independent, you actually have dependencies and these maps talking to each other iteratively before you get the final answer. And it depends on the algorithm, which is the appropriate model. Here's an example from Judy Chu and a student of mine, Celia. It uses an apple to try to illustrate MapReduce. And so the map here is cutting the apple up to make apple slices and then blending the apple slices to make a drink. So that's MapReduce. So it's actually map. This is a map. This is big data, where the data is the apple, and the information or knowledge that comes out of it is the drink. And if we want to do that in parallel, well, obviously we can cut apples in parallel. We can also make it more complicated by having multiple types of fruit, and that's shown here. We have apples and oranges and pineapples, sliced apples, sliced oranges, and sliced pineapples. The type of the fruit is called the key. The value of the fruit is called the slices, or the actual particular fruit items that we start with. So the mapping here goes from one key value pair to a different key value pair. And then we finally want to join it all together to produce a particular blend, which is a particular set of keys, which we're blending together to make our favorite mixed drink. And this is an example of MapReduce. Notice there is a single big map. The reduction here is the mixing, and we have single reductions essentially. And so this Sam's particular problem is an example of ordinary MapReduce running clearly in parallel, because we have every fruit can be cut in parallel. So the mapping part is purely parallel. And even making the juice is actually, in this case, parallel, because we can reduce the different juice mixtures in parallel.